Okay, so in our last lecture, okay, we were just looking at this anharmonic oscillator. We had seen an example where the parameters are changing if you turn on the interaction, which will be a common theme in our study of renormalization of theories. And then we looked at Casimir effect, which was another example where you get divergences, but you also get finite physical consequences from these divergences. And there was a derivation which I kind of failed. You see, I was saying that at the end of the day, if you have such a system where you basically divide your region, your space into, you have two parallel plates, you add a third plate to somewhat regularize it, so that anything outside of this, these two plates separated by L doesn't depend on A. And so what depends on A is what happens between these two large separated plates. So we just look at those two because eventually, if you want to calculate the force, we have to take the derivative of energy with respect to A. And then the energy of the system was given by this number, which obviously diverges. But if you regularize it somehow, we have seen that here we looked at one possible regularization. We just put a cutoff. The energy, do I have it? Now the total energy is some divergent coefficient constant plus this finite term. And the important thing is the divergent part. You see, the divergent part is, now let me go back. Well, the divergent part is actually this part. That part diverges, but it's independent of A. And so when you take the derivative, the finite part which depends on A gives you a finite force. And then I was kind of trying to obtain a general argument that the force would be independent of our regularization. In fact, what I had obtained was it does depend on our regularization. You see, I had looked at such a regularization. And in that case, I found out that, well, this part over here actually diverges. There's again a divergent force, which, well, kind of didn't make sense. And let me first correct my mistake there. You see, what we are putting a cut is not on the number n, but we are putting a cut on the frequencies. And frequencies are pi n over A. So this pi won't be important. So I will be putting a cut on omega over lambda. So if omega is larger than lambda, this cut will make sure that there is no contribution. If omega is much smaller than lambda, it will make the full contribution. And the physical argument we had was very high frequencies will not, they are the gamma rays, they will not interact with anything, they will just pass through. They won't have this zero boundary condition, so to speak. So, and this would give us pi over A plus pi over L minus A, sum over n, and f of omega is, let's say, pi n over A lambda, lambda being our cutoff. And this function f basically starts from 1, goes to 0, and at some intermediate regions, and we don't really care where it goes to 0. This is what the function f looks like. At some step here. And eventually when we set lambda to 0, infinity, you see all the arguments here would just be f of 0, which is 1. Well, let's see. Let me just calculate the, now we have this sum. And this sum can be written as, well, the first thing that you can think of is just replace the summation by an integration over n. N goes from 0 to infinity. And then let me just make a change of variable. Let me just call pi n over a lambda as my x. So the n will be just a lambda over pi dx. So this summation becomes a lambda over pi squared 0 to infinity dx x f of x. Let me go back. So the total energy, if I just take this term, is pi over a plus pi over L minus a lambda over pi squared, this sum. Now let me just take first L go to 0, L go to infinity limit. Eventually that's what I'm interested in. If I take the L goes to infinity limit, this term becomes 0. And here I have a pi over, let's say, a over pi lambda squared from 0 to infinity sorry, this is E total. F would be just the derivative of this one, so that will bring these squares here. This is F. Let me continue with E total. This becomes what am I missing? The x f of x which I don't like.
Maybe we need the different expression for a minus a rather than a part.
Well, we have this E total is E of, okay, hold on. E of a plus E of minus a, where E of a is pi over a, sum over n, and now if we regularize it, it just becomes f of n over a, pi n over a lambda. So this becomes pi over a integral over the n f of pi n over a lambda, which becomes pi a or a over pi lambda squared dx x f of x. This is E of a when we regularize it. So E total, yes, okay. This is a over pi lambda squared dx x f of x plus L minus a lambda squared over pi dx x f of x from 0 to infinity. Okay, now this term cancels this one. And yes, we have L times lambda squared over pi 0 to infinity dx x f of x. Okay, this is the total. Of course, there are corrections to this one, which will bring me this finite force. And, okay, thank you. Now, the important thing is this part, okay, independent of a, there's no dependence there. Depends on f. Depending on what regularization you use, its value will change. But But that's not really a problem for me because I'm not measuring the energy, I'm measuring its derivative. So the force will be, here I would get my, I will get this correction to this one. You see, to this equality, there is this, the sum is an integral plus higher order corrections to that. Those corrections bring me the force, the Casimir force, and which we had already discussed there. So this is what I couldn't manage to drive, let's say. But now we just have that it's independent of A. It's just a possibly infinite constant. Okay, so general picture. Now, we will be obtaining certain quantities like this one, which might depend on how we regularize our system. They might diverge, and if depending on what you choose f as you take lambda to infinity, you see this integral will be just some number. It will be it might be a finite number, but it will be a number. Fx is positive, x is positive, so it will be a positive number. So if you take lambda to infinity, it diverges. So this total energy, whatever that is, it's a divergent expression. But we will get divergences in our intermediate steps. But the physical quantities, like the force, E total is not what we measure. What we measure is the force. Force will be independent of this regularization because the only requirement we had of this regularization is that f of x should go to 1 as x goes to 0, and it should go to 0 as x goes to infinity, and furthermore all the derivatives should go to 0 at infinity. Those are the only requirements we had to drive the Casimir force. Now, physical things should be independent of our regulator. Well, if the physical quantities do depend on the regulator, then there's definitely something we are doing wrong, like I did. And, well, basically that's it. So any questions up to here? Now, our parameters will be changing. The parameters that appear in the Lagrangian are not the things that we directly observe. Observations should be finite, which means that those parameters need not even be finite that appear in our Lagrangian, but whatever we observe should be finite. And divergences might appear at intermediate steps, which should disappear at the end. So now let's start our discussion. Now, on Monday, in our last lecture, we looked at the phi to the 4 theory. Let's start with the phi cube theory. Which will be, our Lagrangian will be given by 1 over 2 del mu phi squared minus m squared over 2 phi squared plus g phi cubed. Well, this is not a well-defined theory, to be honest. You see, its potential energy is phi cubed. It is neither bounded from below nor bounded from above. It's highly pathological in that sense, but for our purposes of demonstrating what will happen, it serves us good. And the reason why I go from phi to the phi 4 theory to phi cube theory is in phi to the 4 theory, the diagrams we have were these ones. And we also had diagrams like this one for the propagator, let's say. In phi cube theory, on the other hand, I have these diagrams. In QED, well, we have these diagrams. Phi cube the expression we will encounter will be very similar to QED. And eventually that's where we would like to go. That is why let's go to the phi cube theory, even though as a theory, strictly speaking, it doesn't make too much sense because it's not bounded, neither from below nor from above. So let's see, let's look at certain diagrams. Let me look at this scattering. The scattering contribution in phi cubed. What do I have? I have this diagram at lowest order. Then I have basically I have this one. I also have this one. And this one. So these two are the lowest order contribution. This is the next order contribution. So if I would go ahead and write this contribution, you see for the S matrix, the only relevant part will be for me this one only, the propagator, which will be I over P squared minus M squared plus I epsilon. The total incoming momentum is P. When I look at this one, well, this will be P. Let me call this K. This one will be P plus K. So the corresponding contribution will be, I have this propagator, I over P squared minus M squared plus I epsilon. Then I have this loop. Well, K is not fixed. At each vertex, I have I times G. One over K squared minus M squared plus I epsilon, 1 over P plus K squared minus M squared plus I epsilon. And then I have the last propagator, which will again be I over P squared minus M squared plus I epsilon. This is the lowest order contribution. Let's say this one. This is the next correction. Plus, of course, I have all higher order parts. Now let's look at this integral. I have d4k 1 over k squared minus m squared plus I epsilon, 1 over p plus k squared minus m squared plus I epsilon. Oh, sorry, p squared. Now, first thing is, if you look at this integral, it is Lorentz invariant. d4k is Lorentz invariant. All these terms appearing here, they are Lorentz invariant. And the whole integral can only depend on k, on p as a parameter. M is fixed, so I'm not writing it as an argument. It can only depend on p, but it has to be Lorentz invariant, which tells me that the result is a function of p squared only. It cannot depend on the various components separately. And furthermore, if you look at what happens when the components of k are huge, well, then you can ignore m, you can ignore k. This gets contributions of this form, k to the 4, which are, if you just separate the radial integral and the angular integral, become dk over k, which diverges. So although our perturbative expansion, as we have been discussing, assumes that the corrections should be small, if you just have these ones, we have a divergent contribution. But just think of this as some intermediate step, which we will eliminate this divergence later on. But let's see, how can I regularize this and evaluate that integral so that I know what these divergences are? Let's see. There are several tricks we will use. Today's lecture will be technical. Let me just warn you beforehand, we will be discussing how we can evaluate these integrals. What are the tricks we have? Well, one of the tricks we will be using is, first of all, we have to regularize it. It is divergent. There are a couple of things we can do. For example, I can take the derivative of both sides with respect to p squared. That is one trick I can do. Which will be derivative with respect to p mu and times the derivative of p squared with respect to p mu, so it is this one. Now, of course, with divergences, you cannot just take the derivatives as if they are ordinary objects, but remember, we should always regularize it. So once I regularize it, I can just move the derivative inside the integral. So this will become twice p mu. The p-dependent part is the next part. So if I take its derivative, I get p plus k squared minus m squared plus I epsilon squared times the derivative of the denominator, which will be with respect to p mu, it will bring me minus 2 p plus k mu. And if you look at this integral over here, well, you see this goes as k to the 6. For large k, it becomes d4k, k divided by k to the 6. This is dk divided by k squared. This is finite. So it becomes a finite integral when I take the derivative. So I can just work with it. Now, how do we evaluate that integral? Or let me, in general, how do we evaluate these integrals? Well, there are a couple of tricks we use. One of them is this one. 1 over ab is dx, 1 over ax plus b, 1 minus x squared. X goes from 0 to 1. This is called a possible Feynman parametrization. Now, this, of course, this assumes that ax plus b times 1 minus x is not equal to 0 for all x between in this interval. It shouldn't diverge, because if it diverges, if ax plus b 1 minus x is 0 at some intermediate value of x, that integral diverges. Well, let's look at our integral. This is a, this is b, and ax plus b 1 minus x is a k squared minus m squared plus k squared minus m squared x plus p plus k squared minus m squared 1 minus x plus I epsilon. Thanks to this I epsilon, ax plus b times 1 minus x is never 0 within my region. So there's already this I epsilon regularization saves me, let's say. So I can use this trick. Now let's see, let me take this 1 over AB. If I take its derivative with respect to A for, let's say, n times, what do I get? Well, let's see. First derivative will bring me a minus 1. And A will be A squared. The second derivative will bring me a minus 2. Up to minus n times 1 over A to the n plus 1B. Which will be equal to, well, I can take the derivative with respect to A of the integral, which will bring me, well, the first derivative will bring me a minus 2. The second one will be minus 3, minus n plus 1 of 0 to 1 dx x to the power n divided by ax plus b x bar to the n plus 1. Usually these 1 minus x's are defined with a bar. This is the definition. So what do we have? Well, here I have n negative signs. Here I also have n negative signs. So gamma n plus 1, 1 over a to the n plus 1 times b is equal to gamma n plus 2 times 0 to 1 dx x to the n divided by ax plus b x bar to the power n plus 1. Let me take derivatives with respect to b. M times well, again, each b derivative will bring me a minus 1, minus 2, minus m divided by a to the power n plus 1, b to the power m plus 1. Well, on the right-hand side, I already had gamma n plus 2. Now, I also divide by that gamma n plus 1. And now what I obtain is, well, let me write minus 1 to the m first. I'm taking m derivatives. Each derivative will bring me a minus negative integer. What else I will get is n plus 1, n plus 2, no, sorry, this is n plus 2, not n plus 1. N plus 2, n plus 3, n plus m. So 1 over a to the n plus 1, b to the m plus 1, times gamma m plus 1 will be gamma. So this will go up to n plus m plus 2 times the integral. Now, gamma n plus 2 times all of these things plus all of those things will give me gamma n plus m plus 2 divided by gamma n plus 1 times this integral. So in general, 1 over a to the n, b to the m will be equal to gamma n plus m divided by gamma n gamma m dx x to the n minus 1 x bar to the n minus 1 divided by ax plus bx bar raised to the power n plus 2. This is one result we have. Whatever the powers of the propagators, A and B will be just the denominators of the propagators. Whatever they are, we can always write it as a single propagator. Well, if we have three of them, this is 2 dx dy. Let me introduce the third one, x plus y plus z minus 1 times 1 over ax plus by plus cz to the power 3. And in fact, 1 over ab is similarly dx dy x plus y minus 1 over ax plus by to the power 2. Now, these are mainly the things that we will need. Now let's go back. This is what we are trying to calculate, remember. For an arbitrary n and m. Now I can use this Feynman parametrization. Just introduce an x integral from 0 to 1, d4k divided by 2 pi to the 4, 1 over k squared minus m squared x plus p plus k squared minus m squared x bar plus I epsilon to the power m plus n. Well, let me just play around a bit. 1 over. I have k squared x here, and then k squared x bar from the second term, but x plus x bar is just 1. Then I have plus 2kp, minus, plus 2kp x bar from this expansion over there. Then I have, what else do I have? I have plus p squared x bar, the square of that term. And then I have the m squared terms, but they are also minus m squared x minus m squared x bar. That just gives me minus m squared plus I epsilon 1 over k plus px bar squared minus, now plus p, or let me write it explicitly, minus p squared x bar squared plus p squared x bar minus m squared plus I epsilon. I will just combine these two, which will give me this is common, p squared x bar is common. What is left is 1 minus x bar, but remember x bar is 1 minus x, so 1 minus x bar is just x. So we get p squared x bar. Now I can just define k plus px bar as my new integration variable in k integral. This will be just 0 to 1 dx d4k divided by 2 pi to the 4, 1 over k squared, let me just say minus delta squared plus I epsilon. Well, this just looks like a propagator, a single propagator. I just combine many propagators. It's just like this. If I had 3 propagators, I could have combined them into a single propagator. And after a suitable shift in integration variable, what I did was, here I have a complicated expression of k. I just wrote it as a square. In k plus something squared, plus things that don't depend on k, And when I make a shift in my k integration variable, I just obtain an expression that's essentially a single propagator. Of course, this delta depends on x. I have an additional x integral, etc. But for the purposes of this k integral, this is just a single propagator integral. Now then the question is, how do I evaluate this integral? Remember, k squared is k0 squared plus minus the k squared. Well, there are various tricks you can still use to evaluate this integral. One is, let's look at this integral. And I will assume that imaginary part of a is greater than 0. Well, if imaginary part of a is greater than 0, this is e to power I s times a over I times a. S goes from 0 to infinity. Well, since imaginary part of a is positive, when s is infinity, this exponent just is 0. And when s is 0, we just get this is I over a. The only requirement that the a should have a positive imaginary part. Well, let's look at this one, k squared minus delta squared plus I epsilon. It has a nice positive imaginary part. Epsilon we will take to 0 eventually, but from positive side. That is one trick we can use. Well, if you have I over a is equal to from 0 to infinity ds e to power I s times a, just take the derivative of both sides with respect to a, n times the left-hand side will be minus 1 to the n times gamma n plus 1 times I over a to the power n plus 1. The right-hand side will be, if you take the derivative with respect to a, n times you get I to the power n, 0 to infinity, ds s to the power n, e to power I s times a. So you get gamma n plus 1, or 1 over a to the power n plus 1 is equal to I to the n minus 1 times minus 1 to the n divided by gamma n plus 1, 0 to infinity, ds s to the n. Anyway. So this is one trick we can use. Well, another trick that we can use is, this is called the Schrödinger parametrization. Another trick is, let's look at this integral first. You see, this trick I can just use straight away because already what I would like to call as a has a positive imaginary part. So it will work fine. And if I use that trick, the k integrals just become Gaussian integrals which I can evaluate. Well, another trick is, let's look at the zero component integral. One over, well, k0 squared minus k squared plus delta squared plus I epsilon raised to some power. Well, this has poles at k0 is equal to plus or minus square root of k squared plus delta squared minus I epsilon. If I consider the complex k0 plane, the positive root will give me a pole here, the negative root will give me a pole here. Well, delta can be negative, by the way. If delta is negative, there are no poles close to the real axis anyway. But if delta is positive, then these are where my poles are. The poles close to the real axis at least. And I'm integrating over this line. That is where I'm integrating over. Well, complex analysis tells me that if you have a contour in the complex plane, just deforming the contour without crossing any poles or branch cuts doesn't change the result of your integral. So I can just rotate this. If I rotate my contour, I'm not in the counterclockwise sense. I cannot rotate them in the clockwise sense because I will be crossing the poles. But I can rotate them in the counterclockwise sense and nothing will change. So this k0 integral along the real line is equal to the same k0 integral from minus I infinity to plus I infinity along the complex, pure complex axis. Now let me make a change of variables. Let me call k0 I k0e. Why the e, it will be apparent in a moment. So my integral now is I, the integral over k0e, from minus infinity to plus infinity, because of these limits here, 1 over minus k0e squared minus k squared plus delta squared plus I epsilon to the power L. Now I can safely take the limit epsilon goes to 0 because I don't have any poles left. My integral is well defined when epsilon is equal to 0. Where here this ke squared is k0e squared plus the k squared. You see, we were working with, in Minkowski space, with plus minus 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 metric. Now, after this rotation, so-called Wick's rotation, now we are working in the Euclidean space. Now, back to my integral. I'm working on this, trying to calculate that integral. This is equal to I from 0 to 1 dx d4k divided by 2 pi to the 4 minus 1 to the power m plus n divided by k squared plus delta squared to the power m plus n. I just dropped the superscript e. But keep in mind that the k here is the Euclidean form moment. I just make the Wick rotation. Now I will be using another trick, 1 over a to the n is 1 over gamma n from 0 to infinity. This is just, in fact, if you just make a change of variable, if you just called s times a to be your new variable x, this is just the definition of the gamma function. And this I can do if a is positive. But everything here is positive. K squared is positive. So let's me use this trick. Minus s k squared plus delta squared. Now k integral is just 4 Gaussian integrals. I just have 4 independent Gaussian integrals, so this will be I times minus 1 to the m plus n integral over x integral over s minus s delta squared, which is independent of k. What will remain is I will get a pi over s, square root of pi over s from each one of those Gaussian integrals. Well, I have 4 of them. D is 4. Why I didn't put the 4 there yet will be apparent in a moment. And this will be, okay, I minus 1 to the m plus n, 0 to 1 dx, 0 to infinity ds, s to the power m plus n minus 1 minus d over 2, this s. Then I have e to the power minus s times delta squared. I have gamma m plus n pi to the power d over 2 divided by 2 pi to the d. Now this integral I can evaluate. This is just the gamma function. So 1 over delta to the power m plus n minus d over 2 times gamma m plus n minus d over 2. This is the result of my integral. Now let's go to my original integral, by the way. What I was looking at this integral, where m and n, they are both 1. This is I times gamma 2 divided by 2 pi to the d. This is the result. Now, if I put d is equal to 4, you see this term? That is gamma 0. It diverges. But for an arbitrary d, it looks like it has a nice analytical answer. And that is basically what is done by dimensional regularization. You see, if you look at this integral over here, in fact, if you put d is equal to 4 or larger, it will diverge. It will diverge because this will become a negative power, the power of s will become negative, and it will diverge at the lower limit of integration. If d is less than 4, it is finite. So what we do is replace all our integrals by their d-dimensional analog. Now, there's a problem though. If you just change that integration variable from 4 to d, you are also changing the mass dimension of that integral. That's usually not something you would like to do. You would like to keep the mass dimension constant. So what you do is you just multiply it with mu to the power 4 minus d. What is mu? Well, some arbitrary parameter. Some arbitrary number with dimensions of mass. Well, if I do that, the integral that I was looking for, if we go all the way back, this integral, in dimensional regularization, it becomes mu to the power 4 minus d which will be given by this expression. And in this form, as long as d is not an integer, well, it's finite analytical. So although we started with a d-dimensional integral, d was the number of dimensions, the final answer we obtain is some analytical function of d, and that is what we use for the value of the integral, value of this expression, whatever the value of d, not necessarily the integer value. In fact, what we do is we just set d is equal to 4 minus epsilon. Why? Because if you have integrals like this, they converge at dimensions less than 4. When d is less than 4, that's why we set d is equal to 4 minus epsilon. And then, for example, gamma 2 minus d over 2 will be just gamma epsilon over 2. And gamma epsilon over 2 has this expansion. It is 2 over epsilon minus some numerical value plus some numbers of the order of epsilon, which goes to 0. So this is the Euler number. It has some numerical value. So what we had achieved at the end of the day, we will get such integrals which diverge in 4 dimensions, but in d dimensions, we can separate out the divergence, and there will be finite contributions. And we will just show that we can get rid of these infinities by just changing the definitions of our parameters. Any questions up to here?
I'm a bit confused. I thought we were able to take derivatives and whatnot because we assumed after regularization, after a regulator.
Mm-hmm.
So we were able to do that, and another
Okay.
regulation comes up.
So we will do a couple of things. You see, one thing we did was, okay, so I was looking at this thing. We said that this diverges. So let's just take the derivative. And by taking the derivative, I have this term. It is equal to this number. Now, what do I have here is, well, there's the term proportional to P. I can just take it out. But there's another term proportional to K mu. That I have to pay a bit more attention to because, well, let me just rewrite it explicitly. This will be 2P mu. Well, I already know the answer of, if I didn't have that term, let's say, I know the answer. The answer will be I times M is 1, N is 2, minus 1 to the 3, gamma 3 divided by 2 pi to the 4. I'm just setting t is equal to 4 because it's finite. Then I have the integral over x from 0 to 1 dx. And then I have 1 over delta squared. M plus n is 3, d over 2 is 2, the power is just 1. Then I have gamma of 1, which is 1. Just keep in mind I have to make one correction. You see, within the integral I have minus 2 times p plus k mu. Well, what would have been changed if in this integral that I started with, in this integral, if I had a k mu term, let me follow my steps. If I had a k mu over there, nothing would change up to here. I would just get a k mu term there. But now I make a shift. When I define k plus px bar as my new integration variable, I'm essentially replacing k mu by k mu minus px bar. Now this k mu, that k mu part is odd under exchanging k2 minus k. So that won't contribute at all. That will just give me 0. So the contribution of this k mu in my integral will be just this minus px bar. That will be what is left after k integration. All the other steps would be identical. I would have just taken out the minus px bar out of the integration variable. So I put it over there. The remaining integral will just give me all these coefficients. So what this gives me, 2p squared minus I, gamma 3 is 2, divided by 2 pi to the 4, 0 to 1, the x 1 over delta squared, and p mu gave me this p squared x. This is what is left. This is the result I have. What was delta squared? Now here I have my delta squared is m squared minus p squared xx bar. Just going from this step to this step. Let's see, I have one mistake somewhere. Did I get the power correct? Well, let's check the signs. I mean, the mass dimension. If whenever you see that you have made a mistake somewhere, that's the easiest thing to check. Do you have the correct mass dimensions or not? So you see, the left-hand side, I have a mass dimension of 4 minus 2 and minus 2m. This is the mass dimension of my integral. When I look at my final result, the mass dimension is, this has a mass dimension 4 minus d, and this has a mass dimension of minus 2m minus 2n plus d. So these just cancel. I have a mass dimension of 4 minus 2m minus 2n. Yeah, okay. Well, mass dimensions are correct. Probably I got the correct answer. Okay, so this is what the derivative with respect to p squared of my integral is. It's a finite number, as you said. But even next hour, what we will do is, I have the general expression of this integral now. The result of this integral is given by this one. So I could have calculated the same thing just using dimensional regularization without taking the derivatives. But there's one thing which makes me think that I have made a mistake in my derivation. I will check it in the break. Because if I set m squared equal to 0, you see there is a divergence in the x integral. It diverges still. Let me check it in the break. No, any questions up to here? By the way, there is one mistake is in the powers of pi. I have a pi to the power d over 2 over there. So that will give me 4 pi to the d over 2. That is one mistake I have. Okay, let's give our break and continue after the break. Any questions up to here? So, to sum up, we will have, in every loop, we will have more complicated loops than this one. But basically, you have products of propagators within some integrations. You can combine products of propagators by using what's called Feynman parameterization. This is one example. If you have 3 of them, this is another example. And in fact, generalization to an arbitrary number of propagators is also kind of trivial. For each ABC, you have you define a variable x, y, z, which goes from 0 to 1. You insert a Dirac delta, which makes sure that when you sum them up, it gives you 1. And here you have the combination of A, B, and C with some power. The power is actually dictated by the mass dimension. You see, A, B, C, if they all have the same, they should have the same mass dimension to be able to use this combination. But if they have the same mass dimension, so the integral should have the mass dimension of A cubed or B cubed or C cubed. And this 2 over here is actually gamma of 3. You can just generalize it to 4, 5, or 6 propagators as you wish. And then, once you combine everything within a Feynman within a single propagator term with some power. Well, here I prefer to do the Wick rotation first, and then use this representation. And that gives me the k integrals basically become Gaussian integrals. If you are in d dimension, you have d Gaussian integrals. I know my mistake. Let me just correct my mistake on the way. Okay. Now my mistake is I forgot these factors in one step. I will find it in the break. And okay, so we do the Wick rotation. We have the representation of 1 over a to the n in terms of gamma functions. The rest is just Gaussian integral, which you can evaluate. And once you evaluate the Gaussian integrals, you can integrate over this parameter that you introduced, one of them, and you get a final answer, which looks simple, analytical, and finite. Well, analytical, let's say. If d is not an integer, it will always be finite. For integer d, it might diverge. That is the divergence we had at the beginning, but now we regularized it. You see, when we set d is equal to 4 minus epsilon, we have regularized the divergence. So we separate the divergent part, and then there will be a finite part. So the trick that we need to show, the thing we should need to show is when we calculate physically observable quantities, that divergent part always can be eliminated in terms of other physically observable quantities. That will be our purpose eventually. And yeah, that is it for the time being. Anyway, let's continue after the break.
Bu esnafisi niye etkilemediğini daha göstermedik değil mi?